In this lecture, we're going to look at the types of synovial joints, and a little bit about how they're constructed so that they can do the movements they do. So, synovial joints are classified within that category of synovial joints, we classify them by the shapes of the bone surfaces that articulate against each other. And there are 6 types of synovial joints in the body: ball and socket, condylar, plane, hinge, pivot, and saddle joints. Ball and socket joints are by far the most freely movable of any of the joints in the body. And they're formed from a spherical head of one bone that fits into a fossa, a cup-like cavity of another bone. And because the bone head is spherical, we can get huge array of movements around this ball and socket joint. So we can see flexion, extension, abduction, adduction, rotation, and circumduction, especially if you're a dancer. And you can make your leg make that great big circular motion. Much easier for the rest of us if to do that with our shoulder joint. The ball and socket joint of the hip is by far the most stable. As we've talked about before, the ball and socket joint at the shoulder is a lot less stable because there's less bone surrounding the head of the humerus, and it's got a lot more soft tissue doing that work. Condylar joints, or ellipsoidal joints, are are kind of a modified version of a ball and socket joint. So here is the ellipsoid shape, so it's kind of an oval shape. If we look at it straight from the top, if we look at it from the side, you can see it's kind of domed in the center and slopes away at the sides. That is a condyle. That's if this is toward one end of the bone, that would be a condyle, and it fits into a similar but sort of opposite shape, the negative shape of that depression in a bone. So we see a fossa on the the articulating bone surface that mimics that condylar shape, but in the negative. And if we think about one way to demonstrate condylar movement to you is to hold your hand face up. So you've got the back of your hand, the posterior surface of the hand, laid down against the desktop, and raise one of your fingers. That is a condylar joint that you're moving, especially if you hold stiff the second and third joints there in the finger. So where the first phalanx articulates against the metacarpal is a condylar joint. And it lets you do that teacher, finger wag, like, no, don't you do that. That is what a condylar, that is a prime example of a condylar joint's flexibility. Not quite completely as flexible as a ball and socket, but you still get a lot of nice movement that way. So you get flexion, extension, abduction, adduction, and even circumduction from a condylar joint. It's not quite as smooth as from a shoulder, but it's still circumduction. Plane joints, a plane, by the way, think of geometry, and a plane in geometry is a big flat shape. So a piece of paper lying on a desk would be a plane, would be in one plane. So these are relatively flat surfaces that glide or smoothly slide across each other. And we see plane joints primarily in the carpals and in the tarsals of the wrist and ankle, respectively. And they allow, they're not terribly movable joints. They allow very short little sliding, twisting, back and forth kind of motions. So you might say to me, Chuck, what are you talking about? They're not very movable joints. Look what I can do with my wrist. And you can move your wrist in 1,000 different directions. And the same with your ankle. You can use your big toe and your ankle to write all the letters of the alphabet in cursive, if you like. So why is it that these not very movable joints are allowing so much flexibility and great movement? Well, it's because there are so darn many of these plane joints amongst the tarsals. So there's a lot of articulating surfaces amongst the tarsals or the carpals of the wrist, ankle, or the wrist, respectively. So it's all of those tiny little plane joints that make up the wrist bone that allow all of the great flexibility that we see with our wrist and with our ankle. Hinge joints are built around a bone that ends in a convex surface. So if this is a bone end here, say we're looking at the humerus coming down to articulate against the ulna here. We have a convex surface and a concave surface of the ulna. And so this is the bone, this is also the bone, although I've drawn the ulna way crazy huge. And so we get lots of really smooth range of motion with flexion and extension only. What you don't see is side-to-side movement in a hinge joint. It only works to move a joint in flexion and extension. So the primary hinge joints would be the bones of the knee and of the elbow, but also all of the bones between the phalanges, the phalanx, the first and middle phalanx, and the proximal and middle phalanx, and the middle and distal phalanx, all are hinge joints. Pivot joints are built so that one bone can rotate around another bone. And if we think about the atlas and the axis, the first and second bones of the spine that hold that hold the head and allow the head to rotate. If this is the dens of the axis here, and so this is the rest of the, I'm not drawing a particularly great version of it, but you see hopefully what I'm getting. Then there is, so this is the axis, and then when the atlas fits over it, it's got just this very smooth, slight rounded surface on the bone side, and then there's a ligament that provides, that captures the dens on the other side and holds the dens close to that joint. And that allows this joint, so here again is on the atlas, this is the dens of the axis, and here's the ligament. So we can rotate this joint from side to side, giving the no movement. That joint, by the way, is called the Axial joint. Atlanto for Atlantis, for the atlas, excuse me, and axial for the axis. We see a similar pivot joint at the head of the radius, where the radius, this is the head of the radius here, articulates against the ulna. There's a little notch in the ulna that allows smooth rotation. And then there's a ligament called the annular ligament, and the annulus is a ring, so it's a ligament that makes a ring around the head of the radius, holding the radius against the ulna and allowing the motion that lets you do pronation and supination of the arm or of the hand. That's the radio-ulnar joint, by the way. And then last of all is the saddle joint, also called a sellar joint. The saddle joint is a, it's like a modified hinge condylar joint kind of arrangement. It's difficult to make that comparison completely, but it's referred to as a saddle joint because you have a saddle and then a rider who fits over the saddle, if you will, so that you can get this kind of motion. But the saddle joint, the saddle also, the way the rider is shaped, there's also coming this way, and like if you could imagine movement directly toward you from the screen or directly into the screen. So it allows flexion, extension, abduction, adduction, and circumduction. And there's only one place that we see a saddle joint like this, and that is where the thumb, where the first metacarpal, the thumb metacarpal, articulates against the trapezium there in the wrist. And it is arguably, many would say, that this is the joint that sort of defines humanity with our ability to do. Remember now the joint motion where you bring your thumb to touch the tip of one of your fingers. That would be, let you think about it for just a second. It's opposition when you touch your fingertips together, and reposition when you spread your fingertips apart from each other. That being able to move your thumb in opposition to your fingers allows our hands to be so amazingly flexible and useful as tools to the body. And so there are, some anthropologists who would argue that it's that joint that really defines humanity. Okay, so those are the 6 different joints, synovial joint types, and I've got pictures of them. Well, there's pictures in the book, and there's pictures in your lab handout too, or your lecture notes as well. And then I've got some information about each of the example, or many of the different example synovial joints in the body, and so I really want to encourage you to read through that material, and as well as a little bit of the information about what provides stability in synovial joints. So there you've got it. If you have questions about any of this information, you know how to reach me. So study well, and we'll see you in class soon.